analysis, and there are like numerous things that you can draw from this, just some main aspects. Very interesting is that depending very much on the development of the fuel prices, which we base on the IEA projections, even though we kind of agree with some skepticism on these, it's one of the projections that we have. If instead of rising prices, you assume that the prices stay, for example, constant, you would see a higher share of gas in the model runs than we've observed at the moment. Storage costs actually don't make such a huge influence. Of course, the overall costs, they change, but basically we need a bit of storage, and the battery costs for lithium ion went down already quite a lot. So therefore this, according to us, doesn't seem like a too high obstacle. The prices for PV, of course, have an influence, as we have a lot of PV potential in India, and if the prices do not go down as fast as we expect, we see a bit of more wind. Still, it's still technically possible to do it even at higher costs. Coming to my conclusions in general, what we've seen in our model run, even though some people might say this is not a realistic scenario that will take place, our assumption was we kind of come from Paris, from the meeting there, and the idea was, okay, is it possible to have some models that only run on 100% renewables, or do we actually need CCS with biomass? Do we need nuclear? Do we maybe need coal, gas as base technology? And all scenarios that we've run since then actually prove, no, we don't need them. It is possible to run a 100% renewable energy-based system, not for 2020, but for 2050. And it is possible for the electricity sector, for the heating sector, as well as for the transport sector. Second, it is, of course, easiest for the power sector to do the transformation first. So therefore, we would encourage the establishment of even further renewable energy sources, especially on the global scale, to kind of drive forward the electricity sector, then being followed afterwards by the other sectors. The main energy carriers utilized our model are wind and solar. However, we also will need biomass for certain other sectors, such as heating and transport sector, which need to be included, and we need to be careful that there's sufficient space and water for everybody in the models. You can see on a global model run that, of course, depending on geographical potential, there's certain advantages that you have to use in certain regions and that you have to incorporate. However, there is such a huge variety of renewable energy sources already that we are very optimistic that these are possible. Coming to my last slide, of course, what I'm showing here is at the moment our current research, and we're working on multiple different projects to kind of come up with additional insights on different kind of countries, improve time as disaggregation, additional infrastructure aspects, putting all the data online, so therefore like verifying it through all of you, because you're then more than eager to do your own model runs or contact us for additional cooperations. We want to highlight especially the storage aspects more in the model, and then we're also happy to engage in IPCC processes, etc., to kind of just to increase this modeling forum that we all of us have and that we are all of a part of, to kind of be part of this big symposium on energy scenarios. And therefore, I thank you very much for your attention.
Thank you very much for this presentation. Any questions at this point? Probably we move over to the left side. Yes, please.
Thank you for an interesting presentation. I was especially interested to see the 1.5 Celsius scenario with very low share of fossil fuels with CCS. So of course the key to almost any 1.5 degree scenario is quite heavy reliance on negative emissions. And I didn't hear much about that, so I'm just wondering what your findings say about negative emissions, I guess especially in the second half of the century, which wasn't shown in your initial slide.
Our assumptions are that we want to examine the period only until 2050, and that we kind of agreed on an overall budget which is in line with the 1.5 degree Celsius, and therefore we have no technologies in there that we have the possibility to include biomass and CCS, but in these model runs it's deactivated. So these results that I've shown to you are kind of in line with the 1.5 degrees Celsius target, that we have zero emissions out of these sectors in the year 2050, and then we have no negative emission technologies needed at this point. So these were kind of the assumptions on these runs. If you would kind of include negative emissions technologies, especially in the longer run, like after 2050, you would actually increase the entire budget and therefore allow for additional emissions beforehand. but our idea was kind of to show that it's actually not needed and that we want to see that this is possible.
Hello, Matthias Rehfeld from IIASA. I'm interested in the industry. Could you elaborate on what technologies are dominant in 2050 in your scenario, especially for steel and cement industry, regarding the process emissions that occur today?
The emissions from the industry sector are only partly incorporated. So therefore, for example, for the steel sector, the electricity being needed for the power plants, etc., these are incorporated. And then the heat being needed, high temperature heat is being incorporated, which is then sometimes with power to X. Then we have some parts mostly based on renewable energy-based electricity, basically. But then emissions from the industry, besides that, are being deducted from the entire budget, and therefore we're kind of then focusing on those sectors that we have included until now. However, the industry might be interesting for the future to include, but due to limited data and assumptions, we've kind of deducted them from the entire budget.
Probably the last intermediate question before we move to Paula.
My name is Shunsuke Mori from Japan. I'm very much interested in the future scenarios of energy technologies. If we really implement the intermittent renewable technologies much more, the energy storage technologies in terms of both short-term and long-term are needed. Can your model assess the capacity and the need for the energy storage technologies output? I would like to know the view on the expanded infrastructure which is needed to keep such a large amount of intermittent energy sources.
The model has included different types of storage, heating storage as well as electricity storage, batteries, etc. So the model decides endogenously which model technologies the model wants to expand at which certain time step. And what we see is that especially in the later duration, so the 30s, 40s, we need huge capacities of storage capacities to balance these intermittent renewable energy sources. Additional infrastructure needs such as electricity lines are not yet included but will be incorporated in the future.
Okay. Thank you very much, Pao-Yu, for the answers. We have seen that the electricity sector plays a particularly important role, and so we're glad to move to the last presentation by Paulo Ferreira, please. Paula is an associate professor at the Department of Production and Systems in the School of Engineering at the University of Minho in Portugal. She holds a PhD in Industrial Engineering and Systems, Master of Science in Finance, and also a degree in Chemical Engineering. She's coordinating a research group with a very nice name, which we also see on the logo. It's also a nice logo, Algorithmi. That sounds like a very energy economic approach. And let me, even though I know some of you don't like this remark, let me mention, and I believe in this, that long-term scenarios, technical scenarios, issues like storage, intermittency, etc., are best covered by engineers. The best economists are engineers. Some are mathematicians, and there are also very excellent economists, like we've seen in the session. But I think that having went through your slides and the others, I think we're happy to finalize this panel with an engineering economic approach on electricity. The floor is yours.
Thank you. So firstly, I want to thank the organization for this invitation. I try to present a vision of the Centro Algorithmi. That's our research center in Portugal, in the University of Minho, where we try to address the energy issues under a quite interdisciplinary approach. We have there engineers like myself with some economic background, we have economists, we have people from the social sciences, and we have also very technical engineering, from electronics, from electrotechnic engineering, and we try to mix our expertise and somehow give a contribution to energy planning and to support modeling and electricity decision making. And this is more or less of the vision that I'm not going to show. So I'm not going to show you a lot of numbers or results. I'm just going basically to show our projects, what we have been doing, and what are the challenges that we aim to address, and what are the future, how we see the future, and how we plan to address also the challenges in the future. So just a brief overview of what I'm going to talk to you about, a bit about the challenge of electricity planning, and I will not take long on this because all of you I recognize it very well in the new market design, and I will focus more on the second part, on the electricity scenarios modeling, because that's where I work more, and basically on generation and transmission planning and demand and supply planning. I will approach these two topics separately, and I will explain you later why. And finally, at the end, we're just going to summarize and show some avenues for further research that we think are important, that we are already working on, but we intend to proceed. So in here you can see what we more or less design, what I see are the challenges, which are basically the idea of transition to a low carbon economy in the future. And of course, energy is clearly related with this transition. This is a key issue. So we have the growing role of renewables. We have this trend of electrification, even of less electrified sectors, what used to be the transportation sector. Now the trend of electrification is quite obvious. And we have this last aspect, which is the increasing role of the consumers that are no longer consumers anymore, but they can also have an active role in the market, like prosumers, as participating with demand-responsive approaches. And this, of course, increases deeply the complexity of traditional modeling, where we used to have very separate roles. Each one has their own role. Those who produce used to produce only, those who transmit or roll the networks use only to roll the networks, and those who consume or use the energy use only to be using the electricity. But now suddenly everything was changed, and we have a kind of a mixed approach in this planning and this value chain of the electricity. So we have to deal with this, with new market regulations, with the adaptation of the electric infrastructures and appliances that must be changed in the way to respond to these challenges, and also with new business models that should support us in this transition, always taking into account of the major issues that always guide us, like the security of supply, ensuring that we have an affordable system, and that we ensure to have the public acceptance, which means the social acceptance of our results. So I would say that the key issue is here the electricity, or the trend to electrify the economy, a big trend on this, and the modeling that we have to change, or we have to address this with new approaches on modeling. I will not take long on this because it's with a lot of information in this slide. It's basically just to show what used to be the electricity value chain. It's a very traditional approach, but then we have now changes. We have the increasing of renewables, so we have to need new transmission approaches, new transmission requirements, which may end up, or some people may say that this may end up with higher prices or not to households, but can end up with also low prices to wholesale markets, and we have to assess all these and see if it is relevant or not, and what is the dimension or the relevance of all these aspects in the future. We have also, so we have here the need to improve the electricity transmission system. We have here the further electrification of the electricity of the economy, and so the rising of the electricity demand in the future, the increasing number of prosumers, which are no longer only consuming electricity, are also producing it, so they are part of the supply industry now also. And we need new models, we need technological developments, especially in what concerns smart cities, smart appliances, smart grids, that will help us to manage all this information to make sure that at the end of the day, this information is used the best way to produce the best results for the entire society, including the companies and also ourselves, the consumers, the users. That is the major idea. So just as I said, the idea is that we are changing from this profile, which is very linear, to something that is a bit more circular. And now we are always talking about circular economy. It's not the same, but it's basically this trend of everything mixing together. So it's not those who produce are not only producing, those who use are not only using, and things can be different. We have here different things like the electrical vehicles, the possibility of producing at my own home, the need for grid monitoring and data analysis. All of these with the objective of contributing for diversification, to assess environmental impacts or reduce it, to increase the competitiveness. Those are aspects that always has been present for many years, but now we also have this increasing role of people that are have an increasing participation in the market. And so this must be taken into account. The human interaction became a large part of the system. We have the need for social acceptance. We must make sure that the decisions that we take, the scenarios that we model, the technologies that we develop are actually accepted and well used by everyone. And we have to ensure that also the consumer engagement, because we want consumers to participate in the market, but to accomplish that we have to design the right conditions to make sure that they will actually participate and will understand, and that is a big issue, the understanding of the market, and make it easy to be implemented in practice, this idea of mixing the consumers also in the market. Of course, for this, information, communication and technology development is a crucial issue that must be considered to make sure that you have smart energy products, service, business, everything. And so this is just a summary of what we know that are the regulations for the future of the proposal of the regulation, just to show that they are based a lot on prosumers, on renewables, on storage, on demand response, so on the integration of everyone in the market. And for this we must create new market opportunities. We must make sure that we are able to integrate the consumers in the market, promoting these new businesses. And we have to make sure that we promote also, remove barriers from cross-border electricity between countries. Everything this must be considered now, but also on long-term planning, because most of these aspects, or some of these aspects, frequently are seen as short-term problems that need to be solved in the short term, like the increasing of the prosumers and the increasing electricity distribution or distributed electricity. That is not only a problem on the short term that should be considered on management, but should also be considered on long term for the design of long-term scenarios. So that is, I try here, that's my vision of some key aspects. Those are not the only one. I'm sure you'll find other aspects that are relevant, but from our vision, it's very important to recognize that an electricity system is more than a collection of interconnected technologies. The dynamics across this value chain must be considered in the kind of co-optimization approach, and we use a lot of optimization models to design scenarios for the future, and it's important to address it in a co-optimized approach, which of course increases deeply the complexity of the algorithms and also increases deeply the complexity of the computational effort that must be done. But that is something that should be thought about. And it's something that's why I'm saying that I'm open a bit our ideas for the future, what can be some ideas that can be addressed, and co-optimization is something that is already being considered, but there is a lot to be done in the future also. And we must make sure that we plan across time scales. We must look at the future, addressing or planning for the long term, showing that these long-term decisions will have an impact on the short term. So when you have to make the operational decision making from one day before, we must understand this, and this will affect and should be considered in long term. Again, this will increase deeply our decision making process, but should be considered. And we must take into account all the flexibilities, especially in issues like demand response, interconnection, flexible generation, and storage. All these aspects should be also considered in the future. Not only the technology development from the supply side, but also the technology development from the consumers and the new appliances that they can be using in the future to deal with the new market challenges. And so this is also the key issues, like understanding and modeling energy-related behavior and the consumer's participation in the electricity market. All these are challenges that should be considered. We algorithm, we try to contribute somehow. We don't have an answer to all these challenges, otherwise we wouldn't be here, we would go home, everyone. But we try to have some ideas, and we try to discuss them, to present them, and also to collect ideas from the others that we hear. And we have this issue about generation and transmission planning, because as I said, usually the generation is one problem, and transmission it's another component, and frequently they are addressed by different modeling approach. Someone is planning or working on generation expansion planning, and you have the ones that work in the transmission, working on transmission expansion planning, which frequently is not the best approach, because we have very complex mathematical models, and we know that we have And if you look at from an integrated point of view of the entire system, they may not reach the best solution of the entire system. And so even under free market conditions, under deregulated market conditions, maybe we can find better solutions if we look at it from a more integrated approach. And that is what some authors do defend or do support, is that we should have a kind of anticipatory transmission planning. So we should go beyond what we have, the generation expansion planning and transmission expansion planning, and go to an integrated model that would be generation and transmission expansion planning. Again, looking at it from a more integrated approach. I'm not saying it is easy, because it's not easy to make modeling either in generation and transmission, and if you mix both of them, it's even more complicated. Of course, you are increasing the complexity of the models, but the issue is that probably you get better results, because it's here what I said. Although there are already some tools, and if you look at the literature, you can find some tools about co-optimization, and some authors that are already using it, but the truth is that a truly integrated model that has been applied or it's been tested in real market conditions, it's not yet very common to see. So it's something that could be explored in the future. And it can, when we believe that it can benefit the planning process. Of course, the way we see the market must change, because we have to look at it from the integrated point of view, and then to design the specific policies to make sure that we can accomplish it. And we had already done some work on this. You can see a recent paper from us that was on the applied energy, but it was a very simple, not very simple, but from the approach that we are now going to try, this one was quite simple, because you just tested how the impact of short-term, in this case, the renewable energies, would affect long-term decision making. And we just show that we should include in the models, in long-term models, we should include short-term impacts. And we showed it with some numbers. We can then see the paper at the end. There's no need to be explaining everything. But the major conclusion is something that we all know, is that the impact of renewables variability on the operating conditions of generators, of thermal generators, should be considered in long-term planning. Of course, again, we just looked at the generation side. We didn't look at the other ones. We assumed that we knew the demand, we knew everything. We're just looking at the generation. And we must take into account, as I said, that there are other issues that should be considered, some technical issues, because we know that renewables can also affect the transmission. And so we should take into account if or not, and how much, will generation affect aspects like voltage sags, overloads, frequency variations. All these aspects that are very technical should be taken into account, and we should find a way of putting some values on this and see if it does make a difference or not, and by how much. And that is the idea of the project that we just started, we just applied for funding with the company that was the transmission system operators of Portugal that decided to have a joint work with us precisely on these aspects, because they want to assess how does the renewable energy system will affect some of these risk metrics, and what would be the value of the loss load, and we want to address also what is the social value of this system adequacy, to see what is the social value, put an economic value on these losses, if they exist, what is the amount of them, and put some economic value on this, and include this also on the optimization models that we use. And also, they wanted also, when we work with them on this, try to develop some kind of co-optimization models that were going to be tested in a real electricity system. In this case, in our electricity system, the Portuguese electricity system, to test it, and to test it in the Iberian system, what would be the impact. And for this, our objective of this project is firstly to assess the computational performance, so if we can do it, and what would be the difficulties on implementing it, how can we do it. That's the first aspect, which is very, from an academic point of view, we want to check the model, what is the best approach, what are the best solvers, how can we do it. That's the first issue. Then we want to check what is this performance or the effect of this co-optimization, what is the actual result, if it does increase the electricity system performance or not, or if it's just a waste of time, we're just spending a lot of time doing co-optimization, and maybe at the end of the day the results are not much better than the others. So that's the objective, it's to test it, to see what is the impact, and then after it to design some policy implications with these results. I'm not going to show results because we are just starting. But so I will jump to the other one. I'm sorry, I tend to talk a bit too much. I sometimes forget that I have time. And we also had other work more related with mixing. In this one, it was generation with transmission, and the second work that we are working now is mixing demand response with supply. And our major objective, I had here some results to show that we already did, where we wanted to show basically that if we can manage to have some demand responsive approach, even under the present or the expected conditions for renewables, we can have a reduction on thermal power production with no other changes, just making sure that we have the consumer working with us in the electricity system in a kind of dynamic approach. Instead of using just simple tariffs to consume more in the less in the morning and the afternoon, we just have to have implement some communication strategies to make sure that you have the consumer engage with the producers or the suppliers to make sure that they consume on the right moment. Of course, this will require additional approaches, additional effective smart system. This will require technological development. This will require strong reliance on information communication and technology, everything that must be done, but can support long-term scenarios. And again, we are thinking of going through, passing from a simple generation expansion planning and then demand responsive analysis to mixing it in a combined system. I'm just going to say this is the project that we have ongoing at this moment that supplies these results, but you can, if you want, I can show you later because I'm being pressured with the time. So just for summary and further research avenues, what we wanted to show is that we try to have a vision, not central algorithm, a multidisciplinary vision of the electricity systems. We try to bring a multidisciplinary perspective with different visions because we recognize that we engineers cannot work by ourselves. We need the support of economists. We need the support of people from social sciences because we know, all those that are engineers, we know that we are not the best ones in what concerns social analysis, as you know. So we need all this support. And the idea is to make sure that at the end we try to analyze, try to bring an integrated approach to the analysis of electricity planning, and we make sure that we have planning across time scales, and we include also uncertainty in the analysis and the related required flexibility, demand responsive, storage, everything. Also, the second part, which I did not address, it's also part of our targets, the issues of social and human factor in the electricity market. It is also part of the project that I was going to talk about. Because we do recognize that we cannot go for demand responsive approaches without further understanding what leads the consumers to react. How do they react and why? What are their behaviors? How to overcome barriers? What is the approaches that can be followed to make sure that at the end of the day everyone is integrated in the electricity system. And just, I think it's all, just have the references and some pictures of Guimarães, where it is located, University of Minho, where you're invited to visit us. Thank you so much. I'm sorry for taking more time.
Thank you very much. We just take one or two questions to Paula because we understand we have a rising opportunity cost here in terms of lunch. Please.
Johannes Meyer, E-Control, Austrian regulator. I have one question concerning demand response. I suppose if you want to model demand response, that's one of the most tricky parts of the whole exercise. So my major question is probably you have to try to figure out the added value flexibility provides, because that's the service demand response provides to the system. And thereby, if you have a optimization model, probably you're trying to calculate shadow prices of flexibility, and that's a part of the value chain the final consumers can get access to, and then the question is whether that's enough for them to do it or not. Is that already covered in your model? So the value of flexibility in the whole system, because then afterwards the major question is only whether that's sufficient to trigger really response or not, because I mean, typically then we have to see how the prices go into the market finally. That would be very interested in getting more information about that.
Okay, so no, we have not yet, because the results that I showed, that I quickly show, are based on a very simple approach, because the project just started this year, in the middle of this year, so we don't have a lot of results yet to show. But the simple result that I showed was based only on a simulation approach, not even an optimization. We just simulated in the future, if we could have a demand-responsive approach, how that would affect the renewables, and if it would make easier for renewables to be integrated in the market. So we did not yet use the optimization approach, and I agree with you, the issue of the economic value would be the one of the tricky things to be considered, and we must then put some value on the flexibility. We are working on this at this moment. We did not work on that yet. I'm sorry. Okay?
Any more questions? Are there any questions addressed to other panelists or cross-sectoral questions? Because if that's not the case, then I would suggest that you address them. We're all still here. Klaus, Volker, Pao-Yu, Paula, and that we address this individually, that we move on to lunch. I think we have seen a very broad range. I'm particularly thankful to having introduced the SDGs to this discussion, which comes at an important point of time. I'm also glad that we have this bottom-up perspective. As Pao-Yu mentioned earlier, this is an ongoing symposium. Symposium means we discuss together, and we hope to publish at least 3 of the papers that were produced will go into volume 7.1 of EAP. And I remind you also to the call of papers for volume 7.2 on access, linked to the issue of sustainable development. We need access to electricity not only in the Hofburg, but also in all the villages in Bangladesh. And so let me urge you to participate in the next symposium, which will also be a topic at the next IAE on access. Let me thank all 4 presenters, participants of the symposium, hopefully, and the audience. Sorry for the slight delay, but I think it was an excellent kickoff for our debate, and was also a good kickoff for the Vienna conference. So thank you very much. Have a great conference, and let's continue the discussions bilaterally. Thanks.